Yes, this theorem fits in one video. If we stay organized and avoid turning a clean idea into a swamp. Today we prove the Eckart-Young Theorem on best low-rank approximation. Suppose A is a matrix. But we only want a simpler matrix of rank at most R. The question is, which rank at most R matrix is closest to A? Not a guess, not a vibe, but the actual best one. Write the singular value decomposition of A. Then A is also the sum of sigma I times UIVI adjoint. So the singular values tell us how much of A lives in each orthogonal rank 1 piece. For once, the notation is actually helpful. The obvious candidate is the truncated SVD. Keep the first R singular values and throw away the rest. This gives A sub R. A matrix of rank at most R. The theorem says this obvious guess is not just aesthetically pleasing. It is correct. Before stating the theorem, let us define the two norms we care about. The two norm of a matrix is the maximum of norm Middlesex over all unit vectors x. And it equals the largest singular value. The Frobenius norm is the square root of the sum of the squares of all entries. Equivalently, the square root of the sum of the squares of the singular values. Here is the theorem. Among all matrices B with rank at most R, A sub R minimizes both the Frobenius norm error and the two norm error. So the answer is, keep the largest singular values and delete the rest. Wonderfully brutal. Because both norms are unchanged by multiplying on the left and right by unitary matrices, we may reduce the problem from A to its diagonal singular value matrix sigma. So instead of approximating A by B, we approximate sigma by C, where C still has rank at most R. That is much nicer. For the Frobenius norm, expand the square using the trace. If tau 1, tau 2, and so on are the singular values of C, then a standard trace inequality bounds the cross term by sigma 1 tau 1 plus up to sigma R tau R. Rearranging gives a lower bound equal to the sum of the tail singular values squared, plus some extra squares. So the minimum possible Frobenius error is the square root of sigma R plus 1 squared plus sigma R plus 2 squared and so on. And equality occurs when C equals sigma sub R. For the two norm, use a dimension argument. Since C has rank at most R, its kernel has dimension at least P minus R. The space spanned by ER plus 1 through EP also has dimension P minus R. So the two subspaces must intersect non-trivially. Choose a unit vector x in that intersection. Then Cx is 0. While sigma x only uses the tail coordinates. So its norm is at least sigma R plus 1. Therefore every rank at most R approximation has two norm error at least sigma R plus 1. And equality again occurs for C equals sigma sub R. So yes, one video was enough. The best rank R approximation is obtained by truncating the singular value decomposition. The error is exactly determined by the singular values we discarded. Beautiful, useful, and far more cooperative than many other theorems that demand twice the effort and give half the payoff.